Yeah.
Well, when we were brainstorming for the brewery, we knew we didn't want it to be named after ourselves or our location. We find that kind of generic and boring. So we wanted the brewery to have a personality of its own that we could breathe life into. And we thought one of the differentiators for us was my scientific background. So without being alienating, we wanted to kind of evoke that. So we were brainstorming names like, we really like the feel of Area 51, which hopefully comes through in Category 12. And what kind of clinched Category 12 was when abbreviated C12 reminds me of Carbon 12, which was pretty key to all my mass spec research back in the day. Looked at my share of C12, C13 peaks. So that's kind of the clincher and the backstory of Category 12. All right, I'm Michael Kuzik. I'm founder of Category 12 Brewing with my wife Karen, and I'm just going to walk you a little bit through the brewing process in the back here. So right now we're back here by the malt mill. All our malt comes in 25 kilogram bags, and we hand load each bag into the mill, and we lightly crack the malt to expose the starch granules in the malt. And we use probably about 20 to 30 bags per brew. And that all gets conveyed up into the hopper above the mash vessel. And in the mash vessel, if you come over this way, you can see we've got a false bottom, which keeps the grain from, it's kind of like the frit on a column. Science tip. And then in there we've got rakes and a plow, allows us to mix. And so what we do is we mix the crushed grain with processed water that's quite hot. But we know the temperature of the grain, we know mass ratting, we know the temperature of the water and what volume of that ratting. And so with some simple math, very accurately hit the temperature we desire. There's two separate enzymes in the malt that we target. They're both amylases that break down the malt into like mono, di, and tri monosaccharides. And that's the really simple food for the yeast to convert to ethanol. And so the optimal temperature of each of those, alpha and beta, differs. And so beta amylase has a lower optimum temperature. It's kind of like, I think, 58 to 64. And that one can produce very fermentable sugars, so a lot of like the di and mono saccharides. And then alpha amylase is more like 67 to 72 Celsius. And that it can't cleave very well at the branch points in the starch polymer, and so it leaves behind more dextrinous, non-fermentable sugar that leads to a little bit of residual sweetness in the final beer, or what we call body. So if you're really, depending on the style of beer you're trying to make, you're trying to play towards dryness or lack of sweetness, or full body and some residual sweetness. So that process takes 60 to 90 minutes. It looks like oatmeal once it's all mixed up. Then we let it rest, and then it trickles off the bottom. We pull it off really gently, just by gravity, into this branch right here, which then fills up and then gets pumped into the kettle. And then the kettle takes about 90 minutes to fill, so it takes about 90 minutes to trickle all that sweet liquid off of the grain bed. And then on the kettle, we boil for anywhere from 60 to 90 minutes as well, and that's where we add our hops. So the boiling serves a few purposes. One is to sanitize the liquid, get rid of any wild microbes. And the second is hops. So if we want to get the bittering component of hops, we add them very early in the boil, and that allows isomerization of the alpha acids into a soluble form. That leads to that bitterness that you know from IPAs. And it's also got an antimicrobial quality, which is really nice. Now, toward the end of the boil, when we add hops, we're focusing on the aromatic component of the hops, which is the essential oils. Limonene would be an example. I believe they're all terpene derivatives. Don't quote me on that, but I can never quite keep the alpha acids and the essential oil structures quite separate in my head. And then those aromas give you the really fruity and floral and sometimes piney and resinous aromas that you're used to in an IPA. So those are the real two key components of that biochemically from hops. And then once we're done boiling, we get the whole vessel whirlpooling, and that, because also during the boil you get a lot of denaturation of the proteins, and then they coagulate and they become insoluble. So we don't want that in the fermenter because it can affect the generate off flavors during fermentation. So by whirlpooling, all of that collects in the center of the kettle after we stop whirlpooling and rest for about 10 minutes. And then we pull off the kettle on a cork that's off to the side, avoiding the trube cone, we call the insoluble matter trube. And then we empty the kettle in about 30 minutes, and it all gets pumped through process piping through this heat exchanger, which allows us to knock it down to least compatible temperatures, from like 100 down to 18 Celsius. And then we recapture the hot water, because it's like a radiator, so it's a counterflow chiller, back into our process hot liquor tank, so we can use that on the next brew. And then immediately after the heat exchanger, we have a sintered stone and we tee in pure oxygen. And so this is really key for cell division, sterol synthesis for cell wall growth, for cell growth and cell wall synthesis. And that is done right on the way. So this brew hose will be connected up to the bottom of one of our fermenters around the corner here. Right now we're in the cleanup phase of the brew day. So now we're setting up into a clean in place loop, which uses 60 Celsius, roughly 2 to 3 molar sodium hydroxide. So it's pretty nasty, but it works very well. And then we then go to the cellar, where fermentation takes anywhere from 4 to 10 days, depending on whether or not it's ale or lager, and then maturation time after that prior to packaging.
Our group collaborated with Dr. Michael Cusick, the owner of Category 12 Brewing, to determine the amount of ethanol in beer that had been aged in wooden barrels, accounting for evaporation that occurs in the barrels. We analyzed 2 different barrel-aged beers, one being an oak barrel-aged imperial stout with its alcohol percentage stated at 10.5%, and an oak barrel-aged barley wine with its alcohol content stated at 11.7%. The goal of our first experiment was to determine the alcohol content in each beer volumetrically, and this was done by Luis. The first thing that had to be done was to decarbonate all the beers to ensure that our results weren't impacted by any air remaining in the sample, and this was done by stirring the samples at moderate RPM for 45 minutes. We then prepared the distillation sample with beer and some distilled water in a distilling flask. A 3-way adapter was used to connect the flask with a thermometer on top, as well as a condenser, as well as a hose connecting from the water spigot to the lower arm of the condenser, forcing cold water to travel against gravity through the condenser. A vacuum adapter was also connected to the other end of the condenser. This was the setup of the simple distillation used in the experiment. Temperature control is critical for distillation experiments, so both a heating mantle and a water bath on top of a hot plate were used to regulate the temperatures, depending on the volume that was used for the experiment. Aluminum foil was used to cover the area around the 3-way adapter to avoid heat flowing out of the system, and this allowed the temperature to rise quickly to the 78 degrees Celsius, where it remained steady and the distillation occurred. The distillation of beer 1 lasted 5 hours and resulted in 7 milliliters of distillate, while beer 2 lasted 2 hours and 10 milliliters of distillate were collected. The next step was to calculate the density of the distillates collected, but as a digital density meter was not available, we had to measure the density manually. To do so, the average weight of the distillate samples as well as the distilled water samples were then calculated, which we then used to determine the true specific gravity of the beers. The true specific gravity of each distillate was converted to the alcohol percent by volume in the distillate, and these values were determined to be equal to the alcohol percent by volume, and the final results were achieved from these calculations. The alcohol content of the oak barrel-aged Imperial Stout beer was determined to be 10.2%, and the alcohol content of the oak barrel-aged barley wine beer was determined to be 11.2%. Both of these values were lower than their respective literature values, being 10.5 and 11.7%. There are several reasons that could explain the difference between the literature and experimental values, one of them being temperature control, as it's not recommended to use a water bath to heat the flask since it's harder to apply heat equally and also harder to control the temperature. Secondly, ethanol and water form an azeotrope at 95.6% ethanol, and this means it's impossible to extract pure ethanol by simple distillation. Finally, a digital density meter is recommended for the measurements because of its higher accuracy, and as we were unable to get access to a digital density meter, our results weren't quite as accurate as expected. Our next experiment involved determining the ethanol concentration in the different beers using UVIC. The first step was to make ethanol standard concentrations to be able to generate a standard curve on the UVIC, and this was done by measuring out volumes of ethanol using an Eppendorf pipette and diluting them with deionized water to our desired concentrations. We then diluted both of the beers so that they had ethanol concentrations within the range of the standards that were used to make the calibration curve. As ethanol itself doesn't show up in a UVIC scan, we needed to add a non-toxic metal ion that would show up in a UVIC scan. So we added copper to each of the solutions to be able to get a visual on the UVIC. Using the line equation for the calibration curve that was obtained, we were able to get the concentration of the ethanol in the beers in parts per million, and then work backwards to get the percent ethanol in the starting beer by accounting for the dilutions done in the sample prep. The ethanol concentration that was determined for the oak barrel-aged Imperial Stout was 11.79%, and the ethanol percentage determined for the oak barrel-aged barley wine was determined to be 13%. Potential sources of difference between the literature ethanol values and the experimental values were that there could have been potential interference from the water within the pentahydrate starting complex, as well as the slight variation in copper concentrations within each sample. In conclusion, while the previously mentioned sources of error could have contributed to our findings, the results showed minimal deviation from the intended alcohol content, and that beer aged in oak barrels for 1 year at Category 12 brewing do not lose a substantial amount of alcohol content during aging. We would like to give a huge thanks to Category 12 and Dr. Cusick for partnering with us to do this project and leaving us with such a positive experience.